Thank you very much, Ron, and especially for organizing the TechBleak for this nice forum again. I really follow the presentation of my former colleague here, to say something about the materials and how we print the materials, especially the quantum dot materials for color converter. And as you can see here from the people that are involved, that's a really international work, especially with our colleagues in Korea. And I hope we can also present some latest result from the lab, which are shown in the end of the presentation. I will give you a first introduction, then I will say something about the quantum dot design, about the green and red quantum dots for PL applications, and of course the 2D printing. So the topics at Fraunhofer IAP, and I will not go more in detail today about our institute, but that is well known that we are working very long time on the topic of organic light emitting diodes. And we start our activities of indium phosphide quantum dots in 2009. And we also introduced our own high precision EHD jet printing last year. So with the high accuracy and also with the high or with a lot of possibilities for introduce this type of materials in the display area. And as you can see here, we started in 1994 with really very simple OLED. And now in last year, we could present our first red and green printed quantum dot for color converting on micro displays. Yeah, what do you need for quantum dot displays? On the first, I think you have to create the right material. I think to tune, and that is a very, very nice property of the quantum dot, you can tune your emission wavelength by the size of the particles. So that is a very nice property of these materials instead of other type of materials which are normally used in displays, in OLED displays, where you need for each color a separate organic material. The second one is to create the right device structure. And I today only will concentrated us on the photoluminescence properties of the quantum dots, but also very nice application of the electroluminescence quantum dots. And of course, in my talk, I will also explain something about our electrohydrodynamic jetting or inkjet printing of our quantum dot materials in our pilot line at Fraunhofer IAP. We are working not only in the device structure, we are looking also to the right synthesis of the materials, especially design of the core and also of the multi-shell. I think it's very important. And in the case of printing of this material, the ligand structure and the ligand shell is very important to adapt this material to a matrix material, for example. And that we do not only for quantum dots, we do it for OLED, but also for perovskite and for other application in the field of energy harvesting of about organic photovoltaics. Yeah, what I can say about the quantum dot where we are concentrated as. We developed several years ago a multi-shell setup of our quantum dot, especially for the indium phosphide quantum dots or the zinc telluride selenate quantum dots. That consists in core and two different shells. Why is it possible? Why is it necessary? I think the different shells are necessary to adapt the lattice mismatch between the core and the shell. And the other one is that to reach a very high internal quantum efficiency, I think it's very important that you have no defects on the different shells and to protect the shells from the environment. The organic ligand is necessary to protect the particles against the agglomeration. And as you can see on the right-hand side, that we can tune exactly, wavelength exactly, emission wavelength exactly, the emission properties. These are two examples of our quantum dots, I think, which we use for the different wavelength range. I think with the indium phosphide quantum dots, I think we can cover the wavelength range between about 500 to 700 nanometers. Especially for the blue emitting quantum dots, we use or we can realize emission wavelengths